may even be going to other universities. I'm not quite sure how that works. The graduate courses, other member universities for the Phoenix Institute. So we're just today, by the way, Nick Rosenblum is talking at 4 o'clock. When we have visitors, they sign up faculty members to chat with them. So I got to talk to them a little earlier today. It's actually, I mean, it's wonderful stuff that he's doing. He and the many collaborators. But no buts. I mean, I don't know. I assume he's a good lecturer. It's a strange business what he's doing. It is the Langlands program, as I mentioned before, not over a number field or rational numbers, but the Langlands program over the field of meromorphic functions on a Riemann surface. At least that's the underlying setting. But it's very unusual and very, to my old-fashioned way of thinking, it's very, I guess it's pretty current now, but a lot of mathematics is phrased in terms of what are called N categories. N categories. And those are, it's category theory, which category theory run wild, say. But the results, I don't imagine he will hit us with too much of that on this lecture. I hope he makes it. I think he's supposed to be a pretty good lecturer, but there's so much deep stuff in it, and it's hard. Must be hard for him to figure out where he's going to start. And categories are an extension of category theory beyond ordinary categories. A category has objects and morphisms, and two category has objects, morphisms, and two morphisms, not two dash morphisms, which are morphisms between morphisms. And three category, I guess, is one that has two morphisms and three morphisms. And it all seems a bit bizarre, but apparently I have read that it is one way to justify it or describe it is it's an attempt to formulate in precise terms or more general terms the advances I don't know much about the homotopy theory, this old-fashioned homotopy theory that people study in first course in topology, the advances in homotopy theory that have taken place over the last 40 or 50 years. Very roughly speaking, what they do is, it turns out you get more deeper in information about homotopy theory and about categories if instead of just taking two loops and identify, saying that they're equivalent, if there's a homotopy deformation of one to the other, they keep track of the deformations. So in other words, they keep track not just of equivalence classes loops in a manifold, but rather equivalence classes of loops together with the choice of equivalence from one to the other. They don't just say there is an equivalence, they actually keep track of it. And those are the two morphisms. And then they keep track of equivalences between equivalences. And that seems, for me, it's very confusing. And I don't know. I guess you have to sort of think about it a lot, or maybe even be born with it. I don't know. But apparently, very deep information comes that you don't get others when you keep track of these things. So this it's not just in ecology, but so the papers of Rosenblum, which have 5 or 6 authors, are formulated to a large extent, to some extent at least, in terms of N categories, but they pertain to quite specific and concrete things having to do with algebraic geometry and the Langlands program. All right. Let me just, so I'm still doing I'm still doing my sort of really just general introduction to what's I hope intuitive terms as to what's involved in the Langlands program. So I mentioned number theory and the question of factoring an integral polynomial mod p. And so then if that's the case, so we agreed that there was, if you have such a polynomial, what comes with it is so given a polynomial, right? This would be the factorization mod p. And you would take almost all primes that do not divide the discriminant of f. And so then what you get is you get a map from primes so S is the set of primes which, let's say, divide the discriminants, and so these are primes that are not in S to partitions. Pi of n. Well, that's very agreeable. It's a very nice sort of concrete thing that one can keep in mind, one can imagine. And it has limitations because it's a little more, there's a little more structure to what we're really looking for than just that. But it is a good way to motivate, for reasons I will say, to motivate the questions that you would be interested in number theory. We start with the premise that we would like to understand number fields, finite extensions of the rational numbers. What could be more basic than that? For integers are things that we're born with, and the rational numbers aren't too much beyond them. And then you got equations, in a higher degree, and the solutions of that. It's pretty close to what foundations of mathematics one would imagine. And so I could pose, let me just in really general terms, just say two fundamental questions. Okay, one. So just sort of in keeping with what I was saying for the Riemann zeta function before, two fundamental questions. Is there an independent way to characterize the pre-image maybe I could call it the capital P of pi, the set of all primes not in S, such that pi p equals pi. So given a partition, if this is a map, so this would be goes to what we call the image of a prime partition P. Primes partitions. Is there, I mean, this is a pretty concrete thing we're talking about to begin with, but it's not really what we're looking for. We're asking whether there's an independent characterize the set of primes, just give a given partition. And in keeping, this is not what we're going to be doing, but is there a sharp S? So that's kind of like the algebraic problem. And here's the analytic problem, like in the Riemann zeta function. Is there a sharp asymptotic? estimate? for? Well, for the things that we were thinking of, for the Riemann zeta function, we were thinking of all primes, but why don't we say, we could call it capital pi x, pi of x. So this would be fixed partition. Very bad notation. No, this will be little pi of x, which is prime. Little pi x, capital pi, namely the set of primes p, which give rise to this given partition. So this would be prime less than or equal to x. This is what the Riemann hypothesis would give you, not for pi, but where pi of x is the set of all primes less than or equal to x. So if we have some sort of, if we're thinking of some sort of characterization of the free image of a given partition as a bunch of primes, presumably infinite, then we could ask the same question we did for the Riemann hypothesis: is there an asymptotic estimate for those when x gets very large? So that's dreaming, but let's say the Langlands program concerns one directly and two indirectly.
So, sorry, may I ask about the notation? So
Yeah.
pi sub p is a partition associated to a specific prime number p?
Yeah.
And which partition is it?
Oh, you're given a partition.
Oh, so
Given capital pi, it's constant. Given a partition capital pi, and take the free image of that under this mapping.
right. So you look at all the primes which would give you this partition,
Yes.
right?
And is there some way to, when you factor the given polynomial mod p, some way to characterize that set of primes?
Right.
There's some way to characterize it.
Right.
Independently, of course, of factoring the polynomial.
I see. I was just like a pi sub p. When you index by p, what do you mean by indexing by a specific prime?
Oh, I'm calling the map that sends p to pi p. Cross on it. Yes, I didn't very clear that you have a map. This will flow from primes, partitions.
Oh, I see. That was just the notation for the partition given by this map.
That's right.
Oh, right.
Maybe not very good notation. So
Thank you.
Yeah, so it gets polynomial. Got a polynomial, you can factor it mod p. It'll give you a partition of n, determining the irreducible constituents of factors of the polynomial mod p. And then, you know, what are the set of primes that give rise? There are only finite many polynomials. So what are, you know, for all primes, almost all primes will this map. Any way to characterize a set of primes that go to a given partition. And that, as it turns out, is that, well, it's in somewhat simplified form, but that is a fundamental, that is a fundamental question. That's almost like non-abelian class field theory, as we'll see. So the Langlands program, this bears upon this. And actually, I think, I don't know, the mathematicians would be unhappy with me saying indirectly, but as I said last time, there are some rather provocative suggestions that seem to be related to analogs of the Riemann hypothesis for these things. But anyway, that's not number two is not what we really have in mind for the Langlands program. Okay, so I do have to okay, so for example, I mean, this is very elementary, and I apologize if you've seen this before, but if you haven't seen it before, it's it might be considered sort of remarkable. Suppose that f of t is equal to um, uh, t squared plus 1. So the discriminant of that, uh, as we know, it's b squared. If the coefficients are a, b, and c, if the coefficients and the powers of t, then the discriminant will be b squared minus 4ac. And so that is, the leading term is 1, the b term is 0, and the constant term is 1, so 4ac is 4, so it's minus 4. And so the set of primes S do not divide the discriminant F. It's only the prime 2. So 2 is where you would have repeated factors, not of the original polynomial. That's when the discriminant itself is 0, but when with 2 is when when you would have repeated factors when you factor it mod 2. And so we've agreed to throw those away and leave consideration to the remaining ones. So well, to throw away 2, then you've got just talking about odd primes. And there's 2 kinds of odd primes. There's the ones that are congruent to 1 mod 4 and the ones that are congruent to 3 mod 4. And so the answer, you know very well if you've seen this, but if you haven't seen it, well, okay, that's nice. So partitions um, 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 for so the partitions, well, we're talking about partitions of 2. N is 2. So partitions of n of 2, you can have I equal partition 1, 1, and partition 2. And it turns out that the set of primes which give the partition 1, 1, those are the primes. So odd primes are the ones that are congruent to 1 mod 4 or congruent to 3 mod 4. And so it turns out, so it can show, it's not obvious from this, but I guess it was considered a remarkable breakthrough or a very beautiful result anyway, 200 years ago, more than that. The ones that correspond that give 1, 1 when you factor mod p are the set of primes p, which are congruent to 1 mod 4, and p set of primes which give 2 the set of primes p which are congruent to 3 mod 4. So this very nice, and this was discovered by I think Gauss, and so it's a special case. Of Gauss law. a quadratic reciprocity. And people say that when Gauss discovered this law of quadratic reciprocity, he was thrilled and he thought it was sort of one of the nicest things he'd ever done. And he looked very hard to try to see if he could figure out a similarly easy and nice law for cubics or quartics or quintics. But I think it's fair to say he never found one certainly as simple as this. But I'll just remind you, this is quadratic reciprocity, and I won't be proving it. It's certainly well within anybody's, in any course, really, you can prove it, but it takes a number of steps to actually prove it. And so I'll quote it. So you have distinct primes. And I will give the so distinct primes, and then you define what's called the Legendre symbol, Q over P in brackets, and you would define this to be 1 if n squared is congruent to Q, and -1 otherwise. Do I have this wrong? Wonder if it is. Anybody notice? I think I was late last night. Melors, what is the law of quadratic reciprocity? Is it Q? Do I want P squared up here? I think I do, don't I? All cases for Q mod P. Yeah. Should be fine. You want a quadratic congruence x squared congruent to Q. Mod P. For some x. For some x? Yeah. Yes. Yes. X squared is congruent to Q mod P. That's right. For some x and P and Q are. There are supplements for, fortunately, there's not one law quite as simple as this that would cover all numbers, but there are supplements. I think they're called the first and second supplement of this, or Q equals plus or minus 1, or Q equals plus or minus 2. Okay, so given this, which I said, it's often proved in the first course in number theory, but it takes the better part of a lecture, I would say. I think Gauss found many, many different proofs of it, some involving complex variables, oddly enough. And it does seem to bear on this. And if you take this as a given, you can prove this. More precisely, this is, so I have mentioned the abelian class field here, and we are going to be describing it at some point in an example, which classifies the abelian extensions, the abelian Galois extensions of any number field. And in particular, Q. So it's not quite, it doesn't look quite like this, but just as an anecdote, a young mathematician called Sam Raskin, who's one of the authors, the multiple authors of these three papers that Rosenblum is done recently. Sam Raskin, he came and gave a talk here about 5 years ago, and he said the law of quadratic, the abelian class field theory is given by this theorem. And I haven't stated that, but I'll describe it when we introduce the notion of Adele. And it is the same as Gauss' law of quadratic reciprocity. And I know, of course, the law of quadratic reciprocity, but it fits so beautifully into abelian class field theory. And I went up to him afterwards and said, I've never seen that before. And he explained it to me in sort of general terms, why that's true. I guess you have to prove it. And then he smiled at me and he said, he was just a young guy. He said, I'm going to dine out on this. I'm going to be able to tell people at dinner parties that I explained to James Arthur that how quadratic reciprocity is a special case of abelian class field theory. And I was flattered as I was walking away. And then well, I think he's probably going to say that's a little gap in his education. It's an amazing gap in his education. I got to explain to him. So anyway, that's remember this in connection with the abelian class field theory. Lukewarmly, I should say, lukewarmly. But anyway, we'll be describing the law of the fundamental law. I think it's called the Artin reciprocity law for all abelian extensions, and it's closely related to this in the case of quadratic extensions. Okay, now I just have to refine any questions? Yes.
Sorry, can I ask what the result of quadratic reciprocity is? Like we've defined a Legendre symbol, but then what? Like, does this symbol satisfy something?
Good question. It is. Sorry about that. Then you can see I don't seem to really have a grip on this quadratic law, quadratic reciprocity. The assertion is a remarkable reciprocity. Yes, that's the best way to describe it. Between this Q over P and P over Q, they're quite different in their statement, but then the assertion is that P over Q is plus or minus 1 times Q over P. Well, there's a very natural relationship between those two Legendre symbols, even though they're defined quite differently. They do different things in the definition. Whatever it is, it's a plus or minus 1, and the assertion is that minus 1 could be minus 1 over 2. Okay, so P's an odd prime, that's an even number, divided by 2. You're going to get a sign, and then minus 1 to the Q minus 1 over 2. So these numbers, which are very important for relevant to the problems that we're discussing, but they're quite different goals. One tells you mod P for a polynomial involving Q, and the other is the other way around. But the two symbols have this very close relationship, one to the other. That's for most primes, mainly P and Q being on. And then there's versions of it for P or for say q equal to 2. Any other question? Yes,
It would be negative 1 to the power of 2 minus 1 which times 2 minus 1 instead of, let's say, sum.
sorry. Uh, uh, Same thing, it's another.
No, you get this exponentially.
Okay. Right? Is that right? Yeah. Sorry about that. Question? All right. So before one tries to answer the this question 1, we need to refine the question just a little bit. It's a very concrete thing to do, to factor an integral polynomial mod p, and then try to figure out what its splitting field is, that polynomial, in terms of the partition. But it's not quite precise enough. And the real way to phrase the question, one needs a little bit of Galois theory. Or really the beginnings of algebraic number theory to formulate it properly. But let's just, first of all, obvious observation that partitions I, and that's what we're talking about, those are the same things as, well, they're the same things as conjugacy classes in the symmetric group. Well, if the things that we are looking for, namely partitions of n, and we're looking at, for these in connection with the Galois group of the splitting field, then what we're talking about, often, not even usually, the Galois group of the splitting field of a given polynomial is the full symmetric group. So really what we're looking for are conjugacy classes in the Galois group. At least if the Galois field has Galois group, the splitting field is the full symmetric. So I'll just say in particular, if the Galois group, well, this is the Galois group of the splitting field, f of x. So in particular, if that Galois group is equal to Sn, then what do we have? We get a map. And that, by the way, happens much of the time. There are many, many different Galois extensions, of course, with Galois group over Q being the symmetric group on n letters. And if that's the case, then for a given polynomial, f of t, we get a map from primes to be not in S to, well, it's customary to write this map as f sub p, or possibly c, of pi sub p. So this is a map from primes to conjugacy classes. So that's it. and it's as a name attached to the image of this map as a name for a mathematician that's much more recent than Gauss. And it's called the Frobenius. Conjugacy class of P. That's it. So that's pretty nice. You have a map from primes to conjugacy classes in the Galois group. But it's not quite. It's
The equality equal to Sn.
partly.
The equality equal to Sn depends on the way you order your roots.
That's right, but
But after conjugacy class.
it's a conjugacy class which precisely takes care of how you do order the roots. So we're fine as long as we talk about maps from primes to conjugacy classes in this Galois group. But it's still missing something. If you have a polynomial, which can certainly happen and is certainly very interesting, where the Galois group is not a full symmetric group, then all you're going to get then is a map from element from primes to conjugacy classes, not in the Galois, but in the full symmetric. Conjugacy classes in the actual Galois group, there might be several that give the same conjugacy class in the symmetric. And on the other hand, we want this all to be independent of polynomials. The polynomial that you choose, there are many different polynomials give the same splitting field. So there's an ambiguity, there's not an ambiguity, but there's just a piece of information missing here. We really want this to be satisfactory. And indeed, when you can present the problem as I formulated, that's certainly for motivation and for thinking that this is all quite natural. But the real way to do it is to just use a little bit of algebraic number theory, which I will just quote. The beginnings of course, in algebraic number theory actually is a different way to map primes in a given Galois extension to conjugacy classes in its Galois group that doesn't depend on factoring the polynomial, concrete and nice as that might be. The fact comes from the beginnings of algebraic number theory, namely the map P to FP. This would be primes P, not dividing certain finite set of primes S, and FP conjugacy class in the Galois group. So let me phrase it this way: the map from P to FP, and I'm thinking of it as a map from primes to conjugacy classes in the Galois group, is well defined. I'm not thinking of it as a conjugacy class in the full symmetric group, but actually in the Galois group of the splitting field. And it's well defined even if the Galois group G is not equal to the full symmetric group. So algebraic number theory tells you that the sort of algorithm for factoring the polynomial actually has a more precise statement. This is that there's a natural construction. If you're willing to throw away finitely many primes in a given Galois extension of the rational numbers, or indeed for any number field, say, you're willing to throw away finitely many primes, and the remaining primes have a natural mapping There's a natural mapping of the remaining cofinite set of primes into the actual Galois group of the extension. So in fact, this mapping, P not in X, going to something we'll call a Frobenius conjugacy class. Galois. This mapping is well defined, and it depends only, it doesn't depend on the polynomial, and it doesn't depend, it depends only on the Galois extension. In fact, depends only on the Galois extension. E. So I could write E for the splitting field of a given polynomial. The Galois section that you would get if you chose to pick a polynomial over the integers. But in fact, this mapping doesn't depend on depends only on the Galois extension. So that's a very nice, you probably many of you know this stuff. You can either get that at the beginning of algebraic number theory. You get it from ideals, factorization of ideals, and a smaller field in the ring of integers in the larger ideal. So it involves factorization of ideals in the rings of integers of the two number fields. Or another way to do it is to choose valuations and see how choose fix a prime, complete the smaller field with respect to that prime to get a p-adic field, and then tensor the Galois extension by this much larger local field, the p-adic field, and then look at what happens in that extension. Do you break into a completely, just one, is it a direct sum of just one field, or is there several fields? I'm not being very clear about this, but there's two ways to do it, both equivalent from basic beginnings of algebraic number theory, and in particular, say the factorization of ideals into number fields, ideals in the corresponding rings of integers. Did you have a question yet? Yeah, Rafaeli.
Like I just wanted to ask, the way we use the fact that the Galois group is the full symmetric group is that we map this to a conjugacy class in Sn, which is exactly a partition. And so there's no ambiguity here because the partitions of Sn are exactly the partition of the conjugacy classes in Sn are exactly the conjugacy classes in the Galois group.
That's correct.
Right. But in general, we might have many different conjugacy classes in the Galois group mapping to the same conjugacy class in Sn.
I think you're right, and the problem's not as precise. I mean, the phenomenon is not as precise in that case.
Right. And is there a quick characterization of what class you map to? Like if it was not the full Sn, is
I
it?
use without.
I see, but I see.
It's more sophisticated, and you have to use algebraic number theory. I don't think there's any. Well, I don't know of any, but I think if you had a characterization, you led the algebraic number theory.
Right.
Okay. Yeah. Okay, that's the question. That's the problem. That's the more refined version of the problem, and so all right. So we can still phrase those two problems the same way. You know, how do you? Is there some way to characterize the set of primes? Let's say base fields are rational numbers, and you're giving yourself a Galois extension. Is there some way to characterize a set of primes whose Frobenius conjugacy class is a given, is a fixed prefix conjugacy class in Galois. Now that is particularly, I've got 2 minutes, I can just, that problem has a particularly important special case. One says that P splits completely. Okay, but F splits completely over P. If, so now I just would talk about the partition P attached to the given polynomial that we had originally. There's F, and let's say that F splits completely over P if pi P if Frobenius class equals 1. I.e. well, X is congruent to, let's say, X minus A1, X minus AR, mod P. So it turns out that this mapping in that case, the special case, it's the one, it's the primes for which the Frobenius conjugacy class is just 1. You got a Galois group, and then you got a prime, and and then that gives a conjugacy class. This is one where the conjugacy class is just 1. And that particular map, the free image of that set of primes, completely characterizes field extension. So a very strong assertion about what data you need in theory to classify fields. So well, it's a natural way to introduce Langlands program leads to it's weird.